Thank you and the organizers very much for having me. So I'll talk about frame dragging, which is a subject usually prone to misconceptions. And I'll try to clarify some of them. So the first thing I want to say is that actually there are different effects with different physical origins that are usually called frame dragging. One of them is this one here. So consider a spinning black hole and some ring around it. And if the ring is static with respect to the distant stars, then it will have a non-zero angular momentum. Conversely, if the ring has zero angular momentum, then it will have non-zero angular momentum with respect to the distant stars. So let's see how these things work. So consider the line element of an axis-stationary spacetime. Whenever this off-diagonal element here is non-zero, then the observers at rest in this coordinate system will have a non-zero angular momentum, and the value per unit mass is given by this expression here. And this will manifest in some effects. One of them is the so-called Sagnac effect. So imagine that there is an optical loop around the spinning object, and then that we are injecting light beams propagating in opposite directions along the loop. Then the beams will take different times to complete the loop. And the difference in arrival times is given by the circulation of this one form here that we call the gravitomagnetic potential one form. Only the observer with zero angular momentum measure no Sagnac effect. So only for these observers, the positive and negative phi directions are equivalent. But these observers have a non-vanishing angular velocity. We can cast this form of frame dragging as the dragging of the zero angular momentum observers. Another effect that is usually called frame dragging, and actually it is the original one to be called so, are the Coriolis or gravitomagnetic forces that are created by the motion of matter. In the case of a stationary spacetime, the description is especially simple. So we can write the metric in this form here, and then in this notation, the space part of the geodesic equation can be written exactly in this form here, where we have a gravitoelectric field mimicking the electric field. We have a gravitomagnetic field mimicking the magnetic field, and like a magnetic field, it will deflect test particles. And it will cause orbits to precess. It is the so-called lens steering orbital precession. It will also cause gyroscopes to precess. The precession equation is quite similar to the precession of a magnetic type. But see, this is the Fermi-Walker transport law, stating that the spin axis of gyroscopes are fixed to locally non-rotating frames. In other words, that gyroscopes define the local compass of inertia. So what we are saying is that locally non-rotating frames, or in particular local inertial frames, rotate with respect to inertial frames at infinity or to the distant stars. So this is the reason for the term frame dragging of inertial frames. And more generally, we can speak about dragging of the compass of inertia, because the frame does not need to be inertial. And so we can cast this form of frame dragging as arising from the compass of inertia manifesting in the equations in this gravitomagnetic field. So we can talk about different levels of frame dragging corresponding to levels of differentiation of the gravitomagnetic potential. The first level is the potential itself, governing the dragging, the Sagnac effect, and part of the gravitomagnetic Hawk effect. I will talk about this in a moment. Then one level up, the curl of the potential, we have the gravitomagnetic field that governs the gravitomagnetic force, the precession of gyroscopes, and also part of the clock effect. And then another level up, already at the level of the potential, that is the second derivative of the potential, we have the gravitomagnetic tidal tensor, which is the magnetic part of the Riemann tensor. And this governs effects like the relative precession of neighboring gyroscopes or the spin curvature force on a spinning particle or on a gyroscope. Now, the thing is that these effects are largely independent because there are spacetimes that possess only one or two of the levels and not the other. And actually, they can sometimes be even opposing. which I will now exemplify. So consider a spinning body, and the test body is orbiting it. It is well known that the periods of co- and counter-rotating geodesics differ. And the difference in periods can be shown to split exactly into these two terms here. One is the Sagnac time delay. The other one is a term that comes from the gravitomagnetic field. And consider first the case of an infinite spinning cylinder. Okay. In this case, we have a non-vanishing gravitomagnetic potential, but a vanishing gravitomagnetic field. It is somewhat similar to the situation in the electromagnetic current. So there will be a dragging of the zero angular momentum observers, but no dragging of the compass of inertia. And this will cause the co-rotating orbit to have a shorter period. Okay? So now consider a curved black hole. In this case, we have not only a gravitomagnetic potential, but we have also a non-vanishing gravitomagnetic field. And they will act oppositely. The potential will tend to decrease the period of the co-rotating geodesic, but the gravitomagnetic field will do the opposite, because the gravitomagnetic force is repulsive for co-rotating geodesics, and is attractive for counter-rotating geodesics. And it will be the effect of the gravitomagnetic field that will win. So the co-rotating orbit will be overall slower. So this is opposite to the situation around the spinning cylinder. And it is also at odds with that naive dragging picture inspired on the fluid dragging analogy that sometimes we read about in science popularization, but also in some textbooks. For instance, that a spinning black hole is like a whirlpool, it drags everything around with it, or that frame dragging is somewhat analogous to the situation of a rotating body immersed in honey. It will drag the honey and then everything sitting in the honey. This is plain false. Actually, frame dragging in none of its levels originates that type of effects. So in order to see this, imagine that some advanced civilization builds a space station around a spinning black hole, okay? And that the station is initially fixed with respect to the distant stars. Then it will simply remain so, with each edge pointing to the same fixed star, because no gravitomagnetic force acts on it. Gravitomagnetic forces only act on moving bodies, okay? The only gravitational force involved here is the attractive gravitoelectric force, that is the relativistic version of the Newtonian force. The only difference to the situation where the black hole is not spinning is that the station has non-zero angular momentum. And this will manifest if there is, for instance, some optical fiber along the station, then a Sagnac effect will be detected on it. And now imagine that the crew starts throwing objects. So they first drop one test particle from rest. As it starts falling, it will be indeed deflected in the direction of rotation of the black hole, because this is the direction of the gravitomagnetic force in this case. But if instead one throws a particle with an initially outwards radial velocity, then it will be deflected in the direction opposite to the black hole rotation. And these lines here are actually the numerical trajectories. So, and this contradicts the naive body dragging picture. But perhaps the sharpest example against this notion are the equilibrium positions for test particles that exist in some black hole spacetimes, like Kerr-Sitter and Kerr-Newman. Starting by Kerr-de-Sitter, it is well known that there is a radius called the static radius, where the cosmological repulsor exactly balances the gravitational attraction. So if we place a test particle there, it will remain at rest forever. No gravitomagnetic force will act on it. And more or less the same occurs in Kerr-Newman for charged particles. For suitable charges, there will be equilibrium positions where the electromagnetic repulsion exactly balances the gravitational attraction, and then the test particle just stays at rest there. So again, this illustrates how different Coriolis or gravitomagnetic forces are from viscid type forces, or in other words, that the dragging of the compass of inertia is something very different from dragging of test bodies. We should really be very careful.
There's 3 minutes left to the talk.
Okay. We should really be very careful with this fluid dragging analogy and the associated body dragging misconception, because sometimes it can even lead to the exact opposite of, it can even predict the exact opposite of the real situation. And an example is what happens in binary systems with the bobbins. So consider an extreme configuration, which is a pair of nearly identical black holes with spins anti-parallel and lying along the orbital plane. It is known, in this case, from numerical simulation, that the whole binary, that is the center of mass of the binary, oscillates up and down along the orbit. And an explanation for this has been proposed based on the fluid dragging analogy. So, according to this picture, the situation would be that when the spins of the black holes are orthogonal to the axis connecting them, the dragging forces would be maximized. So each black hole will drag the other inwards the plane in this phase here and outwards in this phase here. And the drag forces would be zero when the spin of the black holes is aligned with the axis connecting them. But the gravitomagnetic field produced by spinning bodies is dipole-like. Actually, to the leading order, it's very similar to the field produced by a gravitomagnetic type, by a magnetic type. And the gravitomagnetic force that each black hole exerts on the other is given by the cross product of the relative velocity by this gravitomagnetic field. So what we have is that the gravitomagnetic forces are actually maximized when the spins are parallel to the axis connecting the black holes, dragging each other outwards, inwards the plane here and outwards here. And the forces vanish when the spins of the black holes are orthogonal to the axis connecting them, because in this case, the velocity is parallel to the gravitomagnetic field. So it is the exact opposite of the prediction by the fluid dragging analogy or the body dragging picture. And still, this is not a full story, because taking in account only the gravitomagnetic forces will lead to a wrong bobbing amplitude, because these are not the only spin orbit forces in the game. There are also the spin curvature forces that each black hole exerts on the other. That is the forces that come from that third level of frame dragging that I talked about earlier. And these forces have the same form as the gravitomagnetic forces, but opposite direction and a different factor. Actually, in the post-Newtonian scheme, they form pairs of action-reaction, but they do not exactly cancel out. So spin-orbit interaction do not obey an action-reaction law, and this is what causes the whole binary to bob up and down. And notice that no violation of any conservation equation is involved here. Actually, this is just a consequence of the interchange of momentum between the bodies and the gravitational field, in the sense of the Landau-Lifshitz pseudo-tensor. And this is closely analogous to the situation in electromagnetism, that electromagnetic forces do not obey an action-reaction law because the bodies exchange momentum with the electromagnetic field. So, concluding, under the label frame dragging, there are actually different effects with different physical origins that are independent and sometimes even opposing. And importantly, none of them is dragging, because what are drag are the zero angular momentum observers and the compass of inertia, never test bodies. The analogy with magnetism is strong for phenomena related to the dragging of the compass of inertia. And on the contrary, the fluid dragging analogy is misleading in general. In particular, the body dragging picture is wrong. And this generalizes to the exact theory, an analysis, a previous analysis by Ringler made in the framework of linearized theory. So thank you very much for your attention.
Okay, well, thank you very much.